Right, good morning, everyone. Can you confirm that you can hear me clearly? Okay, thank you, Yomelela and Caitlin and Camille. I think we can start. So, good morning, everyone. Welcome to our last lecture on chapter 6, where we are going to finish off what we started yesterday, which is on roots of unity, but I'll start by recapping some things. So we've got our standard form of a complex number. Yeah, z is equal to x plus yi. And then we've got polar form, which is z is equal to r cos theta plus sine theta I. Or we've got the other shorthand where we say z is equal to r e times theta I, like that. Right, and remember that our principal argument is between minus pi and pi, like that. All right, and then we said what is a root of a complex number? Nth root. So let z be a complex number. And n a positive integer. Then we say an nth root of z is another complex number which we are going to call w. Such that we can write w to the n and it will be equal to z. Right. And then, so this is the roots of unity, nth roots of complex numbers, not roots of unity, but of complex numbers. And then we had a theorem which comes in handy when we are looking at this, and that's theorem 6.5.3 in the textbook, which tells us about equality of two complex numbers. So let me write shorthand. So suppose you've got z, which is r1 e to the theta 1I, and then w, which is r2 e to the theta 2I, and then we say z is equal to w if and only if r1 is equal to r2 and theta 1 is equal to theta 2 plus 2 pi k, and this is for some integer k. Right, so that's the theorem. And now we go on back to our theorem, which tells us how to find nth roots of a complex number. So this is theorem 6.5.4. And so it says if you've got a complex number r1 theta r1 e to the theta I, we don't need the one day, and then theta is a principal argument, then if you've got a positive integer n, so we can say n is a natural number there, then you're going to have z has exactly n distinct nth roots, which are given by the formula wk, which is the nth root of n, the nth root of r, e to the theta plus 2 pi k over n I, where k ranges from 0 up to n minus 1. Right, so this is our theorem, and we did step 1, so, and it has three parts. So step 1, we said we wanted to show that wk to the n is indeed an nth root, right? So we've got three parts to the question, to the theorem. Let me just put that in blue. They are indeed nth roots that you are given. They are exactly n and they are distinct. So those are the three parts that you need to prove. And so step 1, we had that. And then step 2, we then said if you have any, because you want to show that these are the only ones, when you say exactly n, you want to say if wk, if w is an nth root of z, then it is going to be one of the ones that we already know. For some k that is between 1 up to n minus 1, right? And then step 3 would be to prove that if you've got any two ones, because now you want to show that all of these nth roots that we have are distinct. Now you want to say, well, if p and q are between these, are in this set, if p is not equal to q, then the respective complex numbers should also not be the same. Then we know that the whole set has got distinct nth roots. Right, and then we did step 1. So proof of step 1 we did in yesterday's lecture. And now we are going to look at step 2, and then step 3 will be left as an exercise. Right, so so step 2, remember we want to show that if you've got any other nth root of z, then it is going to be one of the ones that we already know about. And so we have to start by supposing that we've got some nth root, and we will show that it is indeed. So this is a proof of step 2. So we start off with saying, suppose we do have a complex number that is going to be an nth root, which we are going to call w. So suppose this is an nth root of z with the argument between 0 and 2 pi. This we can always do since we've got this nice theorem that tells us that if suppose the argument is not between 0 and 2 pi, then we can always use this theorem to adjust. We still have the same complex number, right? We can either subtract multiples of 2 pi, or we can add multiples of 2 pi such that it ends up being in the right range that we want for this proof. Right. So we know that by our definition, what it means for W to be an nth root of Z, it means that if we do if we take the power of n, we should get Z, right? That's what it means. But also we know this, so we know this is true by the definition of an nth root. And then this other part, we know this is true by, so this is by definition 6.5.1 in the textbook. And then the other part here is true by de Moivre's theorem, right? Because we know that if you take the power of some complex number, then you're going to take the power and then you're going to multiply the argument by the power, right? Like that, right? So we know this is true. And then we also know that so using theorem 6.5.3, we know that s to the n has to be equal to r. That is given. And one other thing that we know is the argument for this complex number has to be equal to theta plus 2 pi k. Remember, what is theta? Theta is the principal argument for z, right? So maybe let me say principal argument of z there. Right, so we know this is what it means because we are equating z. So just to illustrate, this is r e to the theta I. So by equality, by theorem 6.5.3, if this complex number is equal to that one, then it means their moduli are the same, and then their angles differ by a multiple of 2 pi. That's what we are told in theorem 6.5.3. Right. So what it means is S has to be equal to the cube root of, sorry, not the cube root, but the nth root of R. And so we are just using this to get that. And then here we can then say alpha is equal to theta plus 2 pi k all over n. And this is for some integer k. Right. So here at this stage, if we look at the type of complex numbers that we have, this part we have dealt with, right? We have seen that indeed the modulus is equal to that. Now, and then we can see that the argument for the complex number w is of this form, right? So what is left is to show that the k, so we know this is true for some integer k, so what is left is to just show that this other part also holds. That is, the k is not just an integer, but it can be taken from 0 up to n minus 1. That is what is left. The rest, we have managed to show that if w is an nth root, then that part is fine, that part is fine. What is left is to show the last part, which is to show that k has to be in between these integers 0 and n minus 1. Right. So let's now see how we do that. So since we've got 0 less than alpha less than equal to 2 pi. That was a condition that we had there, so we've got that. Then what it means is if I then divide so it means that 0 has to be less than, so if I replace my alpha with what I have there, then I've got theta plus 2 pi k over n is less than or equal to 2 pi, right? And then what it also means is if I multiply by n, it is going to be 0 this side. So I'm multiplying throughout by n, so the middle term becomes 2 pi k, and then the right hand term becomes 2n pi, right? I've just multiplied by n. The sign doesn't change. Why? Because n is a natural number. So remember that n is a positive integer. So when you multiply by n, the sign of the inequalities there doesn't have to change. Right. So that's the first part there. And if I then subtract theta throughout, I'm going to see that minus theta is less than 2 pi k, which is less than 2n pi minus theta, right? I've just subtracted theta from from all the terms, and that doesn't change the sign. And then, but there's something I also know. I know that theta is between these two fellas right here, right? Minus pi and pi. I know this is true. So if I've got minus pi there, sorry, minus theta there, I can easily put minus pi there, right? Because if theta is between minus pi and pi, if I put minus pi there, it will be less than minus theta, which would be less than 2 pi k, which would be less than 2n pi minus theta. And then if I add 2n pi plus pi here, that does not violate anything there. This should be strictly less than that, right? If I add, so if you look at the two terms that I have in the end here, there I'm subtracting theta, and then there I'm adding pi. So whatever the value of theta here, because it ranges from minus pi to pi without including minus pi here. So even if I add minus pi, this whatever term I have here is going to be less than what I have here, right? And so therefore I can rewrite this as minus pi is less than 2 pi k, which is less than 2n pi plus pi. So I've just removed that and that. Right, so now I've got this term, and then if I divide by 2 pi throughout, so if I divide, so dividing by 2 pi, what do I get? So the first term has to be minus pi over 2 pi is less than 2 pi k over 2 pi, which is less than 2n pi plus pi, like that. And then I will get, so for the left-hand term would be minus half, less than, and then if I divide there, I get my k, and then if I divide there, I'm going to have n for the first one plus half. So in other words, we have shown that k has to be between minus half and n plus half. What does this mean? Remember that k is an integer, and also the fact that n is a positive integer, right? So we can say but k and n are integers. So the smallest integer that is less than minus half is going to be 0. And then the biggest integer that is less than n plus half is going to be n. Right? So we can say that k and n, k is between 0 and n with both 0 and n included. Right. So we seem to be almost there, because in our statement, k is between 0 and n minus 1. Now we have shown that k is between 0 and n. So we now want to see what happens when k is equal to n. And then if we can discard that one, then we have shown that indeed it is between 0 and n minus 1. Right. So so when k is equal to n, what then happens? Let's look at the term. So the natural, the nth root of r times e theta plus 2n pi. So we have put so this is when k is equal to n. This is the scenario that we are looking at. That is over n, which is going to be equal to the square root of, the nth root of r e to the theta over n plus 2 pi I, right? So that is our term there. And then from here we can say, but we know that if you have gotten whatever term that you have, or whatever argument that you have, remember theorem 6.5.3, what it says: if I can remove a multiple of 2 pi, I still have the same complex number, right? So in this case, if we are able to remove this, we know that we still have the same complex number. So the nth root of r e to the theta over n I will still be equal to this complex number because of theorem 6.5.3. And then, but what is this complex number here? This complex number is just W naught. So if you think about W naught, this you can put as a side just to see why this is equal to W naught. So if you look at what we are given as W naught here, you'll see that W naught is going to be the nth root of r e to the, so when k is equal to 0, this disappears and then you're left with theta over n I. So this would be W naught. But that's just what we have here. So I just wanted to write here, from the formula that we are given in the theorem, this is W naught. So in other words, Wn is equal to W naught, right? So we don't really need, we can remove one of them because we are talking of the same complex number, right? And so therefore, once we are able to discard n, then it means now we can say that k is between 0 and n minus 1. So in other words, w is going to be equal to wk for some k that is between 0 and n minus 1. And that is the end of that proof. I hope that is clear there, what's happening. If you have any questions, please feel free to post them in the chat. If you have any questions about the proof, and then I will say, so proof of step 3 is left as an exercise. Right. So that is that for that proof. Let's look at some examples and see how we are able to use this theorem. Now that we've got this theorem that tells us how to find all the nth roots of a complex number. So an example, so find fourth roots of the complex number z, which is equal to minus root 2 times root 2 minus 2 times root 2i. And it is you have to write them in standard form. So there's a similar question in the textbook, but it's not exactly this one. So you can go and check out the one in the textbook, but we are going to do a different one here. So let's look at the solution here. How do we look at this? So what we want is to write z in standard form first. No, not in standard form, in polar form, right? Sorry about that. So we want to write z in polar form first. It's already in standard form in this case. We want it in polar form because you know that the theorem that we are going to use uses a complex number that is in polar form, right? So that's the first thing. So we have to find r, which is the modulus of z, which is going to be equal to the square root of 2 root 2 squared plus 2 root 2 squared, right? And if you look at 2 root 2 squared, that's just equal to 8. So 8 plus 8 is 16. So it is the square root of 16, which is equal to 4. Right? And then we want to find the argument, right? Or the principal argument, in fact. So we say 4 cos theta. Again, here you can use any method that you see fit. It will be fine. So this will be minus 2 root 2 minus 2 root 2i. And then if you look at the real part, it tells you that 4 cos theta is going to be equal to minus 2 root 2. I think using the formula for tan in this case would be much simpler, because this will just be equal to, if you divide those, you're going to get 1, and you immediately know that at least the angle is pi over 4. Which quadrant it's going to be in, that's something you need to figure out, but at least you can see that right away that it's pi over 4. It's a form of pi over 4. Right, so we've got 4 cos theta is equal to that, and this tells us that cos theta is equal to, so if you divide by 4 throughout, you get the square root of 2 over 2 minus the square root of 2 over 2, and that tells me that theta has to be equal to 3 pi over 4, or minus 3 pi over 4, right? So the idea, as usual, is we can see that the cos is negative. If we draw a little diagram there, then we can see that it has to be in here or in here, because that's when cos is going to be negative. And the one here would be 3 pi over 4, and then the one in here will be minus 3 pi over 4. And then if you look at the imaginary part, then you know that 4 sine theta is going to be equal to minus the square root of 2 over 2, and that means that sine theta is this is minus 2 root 2, so this is minus root 2 over 2, and again it's negative, so sine is negative, so it's going to be negative in here and in there, and so the one that is common is going to be that one, right? So once we know that, then we can say, therefore, theta has to be minus 3 pi over 4. That is our principal argument, and you can see that it's between minus pi and pi, so we are set. So we know what is theta, what is r, and then we can say z is equal to 4 e to the minus 3 pi over 4i in polar form. Right, now we then apply our theorem. So by theorem 6.5.4, the fourth roots of z are going to be wk is going to be the fourth root of 4, or you can maybe let me just write it as 4 to the minus a quarter, which means it's just the fourth root of 4, e to the minus 3 pi over 4, so that is our theta, plus 2k pi, and then we divide throughout by 4, and then times I, and we know that k is going to be from 0 to n minus 1. In this case, because n is equal to 4, n minus 1 is equal to 3, so we end up at 3. So once we get that, then we are able to find our roots, which should be exactly 4, and they should be distinct. So if I then say w naught, it's going to be equal to, so here if you look at this, this is 2 squared times a quarter to the power a quarter, which is just 2 to the half, which can be written as the square root of 2, right? So we can say that w naught is the square root of 2 e to the, now we plug in our k, so when k is equal to 0, we get minus 3 over 4 over 4, which is minus 3 pi over 16i. That is our complex number, and this is in polar form. You can write in the other polar form, cos minus 3 pi over 16 plus root 2 sine minus 3 pi over 16i, right? And then so if you want to write it in standard form, for example, you just have to find the cos of that and the cos and the sine of that, and then it's already in, it becomes a complex number in standard form, right? And then w1 is going to be the square root of 2 e to the, so when k is equal to 1, we now have 2 pi. So if we say 2 pi minus 3 pi over 4, that is 8 pi minus 3 pi over 4, which is 5 pi over 4. So it becomes 5 pi over 16 I, which you can rewrite. I will not end, I'll stop here. Well, maybe let me write the square root of 2 cos of 5 pi over 16 plus root 2 sine 5 pi over 16i, like that, right? And then we go to the next complex number, which is the square root of 2 e to the, now when k is equal to 2, we are now saying 4k, 4 pi, which is 16 pi minus 3 pi over 4, which is 13 pi. So we get 13 pi over 16I, which is the square root of 2, cos 13 pi over 16 plus root 2 sine 13 pi over 16 I. So let me just point out that I'm not writing them in standard form, but if you really need them in standard form, you just find out what these values are going to be, and then you plug them in, and then you get your standard form. And then the last one is W3, the square root of 2e to the, so when k is equal to 3, then we're now saying 6 pi, so minus 3 pi over 4 plus 6 pi can be rewritten as 24 minus 3 pi, 24 pi minus 24 pi minus 3 pi, which is 21. So 21, and then our denominator is 16i, which can be written as root 2 cos 21 over 16 pi plus root 2 sine 21 pi over 16. And then we've got all the complex numbers. And maybe I should also point out that in an assessment where you're not expected to be able to find this type of causes and sines, you're not going to get that. So Caitlin says, but 21 pi over 16 is greater than pi. That is correct. So we need to adjust that. So we have to subtract 2 pi to be able to get the right complex number. So 21 over 16 pi. If we say minus 2 pi, so it is too big, and so we want to adjust it. So we subtract 2 pi, and then we get, what do we get? 32, no, 32, rather 21 minus 32 over 16, all pi there is going to be equal to minus 11 over 16. I think that is correct. So this complex number, if we are writing this with a principal argument, should be square root of 2 cos of minus 11 over 16 pi plus square root of 2 sine minus 11 over 16 pi. And so thank you, Caitlin, for noting that. And so that will be our complex number with the principal argument there. And that is that. So that is that for that question. So that's how we approach these. You've given them a question, you just have to find the you have to write your complex number in polar form, and then you just apply the formula in theorem 6.5.4 to find all the roots. Okay, let's look at another example quickly, and that is 6.5.6, and it says find all the solutions of the equation z to the 4 is equal to I squared, and so again we start off with finding the writing the complex number in terms of in polar form. So we say I squared is going to be equal to minus 1, which can be written as e to the pi I, because you can find the modulus and the angle if you just draw, and then you've got your minus 1 there. You can see that the argument is there is pi, and then The modulus of -1 is obviously 1. There's a question. If it is too big, we take away 2 pi, and if it is too small, we add 2 pi. So if it's too big, you subtract 2 pi. If it's too small, you add 2 pi until it's in the right region that you want. Okay, so we've got this. So if you want to find the fourth roots of this complex number, then we say z is equal to wk, which is e to the pi plus 2k pi over 4I, and k has to be from 1, 0, 1, 2, 3, and then from here, if you find the complex numbers in standard form, so I'm going to skip the part where you have to put in the k 0, 1, 2, 3. You can easily do that. So maybe let me just say W naught there is equal to W1 is equal to W2 is equal to W3 is equal to that. And you can then say, well, if this is the case, then if you want to write them in standard form, then you can find the actual values. Then you say you see that it will be 1 over root 2 times plus I of that, and then W1 is minus root 2, minus 1 over root 2 plus I over root 2, and W2 is going to be minus 1 over root 2 minus I over root 2, and then the last one, W3, is going to be half minus I over root 2, like that. So you can also draw them in the complex plane. Right, so we will now just look at the last part, which is on nth roots of unity, which is a special case which gives us some nice geometry. So there's a question, please repeat 1 squared is going to be equal to -1, which is e pi I. Okay, so I squared, we know that I squared is equal to -1. If you want to write that in terms of a complex number, you find the modulus of the complex number. Well, you can write this as 0i if you just want to see how it really looks like. So you know that this is 1. And then for the argument, well, if you draw it, you can see what is the argument. So the argument, because -1 will be here, because this will be the real part and the imaginary part, you can see that if we move from there to there, we get that to be pi. So that's why the angle is pi there. You can sort of do what I was doing, finding cos and sine if you want. It's still fine. You just follow what we were doing in the previous questions. If you want to go this route, you can still do it. But if you draw it, -1 is easy. You can see what is happening when you just draw the complex plane. Right, so now we look at the last case, which is roots of unity. So 6.5.7, and we call them roots of unity, right? There we just mean that the nth roots of 1, right? So roots of 1. Let me just put nth there. Nth roots of 1. So the unity is just saying 1, right? And so let's see what happens. So if you write 1 in polar form, again, just following what we did there, the modulus of 1 is 1. So we expect that to be 1 times e. And then the argument is going to be, so if you draw the complex plane there, real part, imaginary part, so this complex number 1 plus 0i will be here, and the argument has to be 0, right? Because it's on the x-axis, the right side of x-axis, so the argument is going to be 0. So you write it like that. So this would be your complex number in polar form. And so therefore, by theorem 6.5.4, the nth roots of 1 are given by wk, which is equal to e. So we know that the nth root of 1 is 1, so we don't need to put that there. And then e, and then 0 plus 2 k pi over ni, right? So we've got 0 as our argument, so we don't need to put it there. So we end up with something that looks like this. 0, 1, n minus 1, like that. Right, so these will be the nth roots of 1. And so we note some things. For each k from 0 up to n minus 1, the modulus of the complex number is always 1, right? If you look at your r here, it's going to be 1. So what it means is, remember, when the complex number, the modulus of the complex number is equal to 1, what it means that is that all the nth roots, since all their moduli is 1, it means that they all lie on the circle with radius 1. With radius 1 and center 0, because the only complex numbers that have modulus 1 lie on the circle, right? So in this case, in this special case where we are finding roots of 1, we see that that is the case. That's one thing to note. And then the first nth root, of this of unity is e to the 0i. So when you put k is equal to 0 there, you end up with 0i, which is just 1, right? So so when you draw that circle there, the first nth root that you have is 1. And in the special case when n is even, we also have minus 1 as a complex number, and it's the complex number that e to the pi I. So when you put n minus 2 here, n over 2 here, you can see that the angle becomes, when k is equal to n over 2, you'll see that the angle becomes pi, right? So we get e to the pi I, which is the complex number minus 1. And so you get that. So part of that is the fact that all the real nth roots of 1 will also be complex nth roots of 1, right? And then there are also, one other thing to note is, if you move from one complex number to the other, they've got their the angle increases with a fixed value. So moving from wk to wk plus 1 along the circle, the argument increases by 2 pi over n. That's one other special thing, and that will be from 2k pi over n to, so the argument for that, and that's what we are just writing here, 2k plus 1 pi over n. So therefore the roots of unity are evenly distributed. Evenly distributed along the circle. The modulus of z is equal to 1. In fact, there's one more thing. They actually make a regular polygon. If you for example, draw so suppose you've got a complex number there, complex number there, complex number there, just as a sketch here. If you join the vertices there, or join the complex numbers, the roots, they make, so this is not the proper one, but the proper one, they would make a regular polygon. So if it's, for example, you've got cube roots of unity, they are going to they're going to, if you join the complex numbers, they will give you an equilateral triangle, and then for any other n, it will give you a regular n-gon, or a regular polygon with n vertices. And just to illustrate this, I've got just some pictures to show you. So these would be the cube roots of unity. So there you would see that we can actually draw a circle. There's no circle, but you can draw a circle around which touches all those 3 points, and you will have this nice equilateral triangle, which will be the regular trigon, right? And if n is equal to 6, so we want the 6th roots of unity, this is what it would look like. So if you plot the complex numbers there, z1, z0, z1, z2, z3, z4, z5, you will get, if you join them, you can see that they make a regular hexagon, and you can see that they are all passing through a circle, or a unit circle of radius, a unit circle with center 0, and that is it. So thank you. This is the end of chapter 6, and tomorrow you start with chapter 7 on polynomials. If you have any questions, feel free to ask about this, what we have just done. Otherwise, enjoy the rest of your day and the rest of your week. I'll be here for a minute or so to answer if there are any questions. But yes, this is the story of complex numbers, roots of unity. All right, I will assume there are no questions, so thank you. Enjoy the rest of your day, and bye.